Hey everyone, ready for another deep dive? Today we're going to unravel a bit of the material world.
Yeah.
See how the structure of a material can totally change how it handles heat.
Right.
Like think wood versus metal.
Yeah.
It can be at the same temperature,
Uh-huh.
but one feels so much warmer to the touch.
Exactly.
That's the kind of mystery we're tackling today.
Oh, okay.
And we're doing it all thanks to this fascinating lecture on anisotropy.
And that difference you feel when you touch wood or metal, it all comes down to how their internal structures, dictate heat flow. Mm-hmm. We're used to thinking of materials as uniform, like they behave the same way in any direction.
Yeah.
But anisotropic materials,
Yeah.
it's a whole different story.
Okay, so let's unpack this anisotropy thing.
Okay.
It sounds kind of intimidating.
Yeah.
But I have a feeling it's way cooler than it sounds.
For sure.
What's the simplest way to wrap our heads around it?
Imagine a highway versus a winding mountain road.
Okay.
So heat flowing through an isotropic material, like metal, it's cruising along that open highway, moving at the same speed in any direction.
Gotcha.
But with anisotropic materials, like wood, heat is taking that twisty mountain path.
Oh, okay.
So its speed and direction depend heavily on the route.
Yeah.
That's carved out by the material's structure.
So it's like the material's internal structure is setting up a heat flow obstacle course.
Exactly. And that's where things get really interesting.
Yeah.
We see anisotropy in a surprising range of materials.
Okay.
From natural ones, like wood with its grain, to engineered materials, like vertically aligned carbon nanotubes, where heat zips along the tubes but struggles to move between them.
Wow.
Even black phosphorus, zinc oxide, and certain metamaterials exhibit this fascinating behavior.
So if it's not just uniform conductivity, how do we even begin to describe and measure this directional heat flow? It can't be just a single number, right?
You're absolutely right. A single number just won't cut it when we're dealing with something as complex as directional heat flow.
Yeah.
We need a tool that's a bit more multifaceted, something that can capture how heat navigates this intricate, obstacle course within the material.
I'm already intrigued. What's this multifaceted tool we're talking about?
That tool is called a tensor.
Tensors.
Yeah.
I've heard that term thrown around before. But I'll admit, it always sounded a bit mysterious.
Well, think of tensors as the Swiss Army knives of physics.
Okay.
Packed with tools pointing in every direction.
Okay, I love that analogy.
Yeah.
So instead of just a single number, we have this Swiss Army knife tensor that can handle the complexity of anisotropic materials.
Exactly.
Tell me more.
So while a single number like thermal conductivity describes heat flow in isotropic materials, a tensor, represented mathematically as a matrix, allows us to capture the varied thermal conductivity in different directions within an anisotropic material. It's like having a heat flow map. But instead of just showing streets, it shows the preferred highways and back roads for heat to travel.
Gotcha.
Based on the material structure.
That's incredibly cool.
Yeah.
So we've got these tensors representing the heat flow landscape inside anisotropic materials.
Exactly.
But I'm guessing this is just the beginning of the story, right?
You're catching on quickly. Now we need to bring another key player into the picture.
Okay.
Fourier's law.
The laws of physics.
Yeah.
I have a feeling things are about to get even more interesting.
For sure. So Fourier's law is like the traffic cop directing heat flow.
Okay.
Always pointing it from hotter areas to cooler ones in simple isotropic materials.
Yeah.
It's pretty straightforward. A single thermal conductivity value tells us how efficiently that heat is moving.
But we're not in simple material territory anymore, are we?
Right. When we're dealing with anisotropic materials, things get more nuanced. It's not just about how much heat is moving. But also about how the material structure is influencing its path.
Right.
And this is where our Swiss Army knife tensor, with all its directional tools, becomes incredibly useful.
So how does Fourier's law work with our tensor in this more complex scenario?
Think of it like this. Fourier's law tells us the heat wants to move from hot to cold. The tensor, on the other hand, lays out all the possible routes within the material, each with varying levels of resistance, combining those two. The law and the tensor gives us an incredibly precise picture of how heat will navigate through the material.
Okay, that makes sense.
Yeah.
So it's not just about finding the shortest distance between hot and cold.
Right.
It's about finding the path of least resistance within the material's unique structure.
Precisely. And the implications of this are pretty remarkable. For instance, simply rotating the material can actually change the direction of heat flow.
Wait, hold on. Just by physically turning the material, we can change where the heat is going. How is that even possible?
Remember, our tensor tells us the preferred paths for heat flow. Based on the material's structure. When we rotate the material, we're essentially changing the orientation of that internal structure relative to the temperature gradient, the direction the heat wants to move.
So it's like turning a map. Your starting point and destination stay the same.
Exactly.
But the route you take changes.
Exactly. Let's take a layered material as an example. Imagine a stack of different materials with varying thermal properties, like a high-tech cake. If we apply a temperature gradient and then rotate this cake, the heat flow will change direction. No longer moving in a straight line, but following a new angled path dictated by the new orientation of the layers.
I'm starting to see how this works. But it still feels a bit abstract. Is there a way to visualize or quantify this change in heat flow direction?
Absolutely. The lecture actually provides a specific example. Taking a laminate with known thermal conductivity values and calculating the angle of heat flow relative to the x-axis after rotating it. By plugging in those values and the angle of rotation, you can predict exactly where the heat will travel.
Wow. So we can actually map out the heat's journey based on the material's properties and its orientation. That's incredible. It makes you wonder, are there any other ways to influence this directional heat flow? Besides physically rotating the material?
That's a great question. And it leads us to another fascinating phenomenon called the thermal Hall effect.
The thermal Hall effect. I'm all ears. Tell me more.
Instead of physically turning the material, imagine applying a magnetic field perpendicular to its surface.
So we're introducing a new force into the mix. What happens next?
This magnetic field can induce a temperature gradient perpendicular to the intended heat path, essentially nudging the heat flow off course.
Whoa. So it's like the magnetic field is creating a detour for the heat. Even though we're not physically rotating the material.
Precisely. It might sound strange. But this phenomenon showcases yet another way. Anisotropic properties can lead to unusual heat flow behavior.
My brain is officially doing a happy dance with all this talk about rotating materials and magnetic detours. But before we get too carried away, I have a question. We've focused a lot on the benefits of anisotropic materials. But are there any downsides or challenges to working with them?
That's a really important question. While the possibilities are exciting, there are definitely challenges. For example, the manufacturing process becomes much more complex. You can't just treat an anisotropic material like any other material. You have to be mindful of its orientation every step of the way.
So it's not as simple as just grabbing a block of wood and carving it into whatever shape you want. You need to think about the grain direction and how it impacts the final properties.
Exactly. It's like tailoring a suit. You can't just cut the fabric any which way. You have to follow the grain to ensure a proper fit. And then there's the challenge of characterization. Measuring thermal conductivity in an anisotropic material is a multidimensional puzzle. Because you need to measure it in multiple directions.
So it's not just about knowing if it conducts heat well. It's about understanding how it conducts heat in each and every direction.
Precisely. And that level of detail is critical for understanding how these materials will behave in real-world applications.
It sounds like working with anisotropic materials requires a whole new way of thinking. Compared to traditional materials.
Absolutely. It's a paradigm shift. Instead of thinking about the material itself, you have to think about its orientation. And how that influences its properties. It adds complexity. But it also opens up a world of possibilities.
I'm starting to see that.
So
we've got this whole new world of possibilities. But it comes with its own set of challenges. Where do we go from here? What's next for anisotropic materials? It feels like we've opened up this whole new dimension of material science.
It is exciting, and the potential applications are vast. Just imagine harnessing the power of directional heat flow to, revolutionize how we design everything.
Okay.
From electronics to buildings.
Okay, let's dive into those applications.
Okay.
You mentioned electronics.
Yeah.
How could anisotropic materials change the game there?
Think about the problem of overheating in electronics. It's a major limitation in how we design and use everything.
Right.
From smartphones to powerful computers. But imagine using anisotropic materials to strategically channel heat away from sensitive components.
But instead of just trying to cool things down after they get hot, we're talking about using the material itself to redirect the heat flow.
Exactly. It's like designing a built-in thermal management system.
Right.
And it could lead to smaller, more efficient devices without the need for bulky cooling systems.
That's incredible. And what about those innovative building materials you mentioned earlier? How could anisotropy play a role there?
Imagine a building that naturally stays cooler in the summer and warmer in the winter, all thanks to the strategic use of anisotropic materials. We could design walls and roofs that channel heat away from living spaces when it's hot outside and towards them when it's cold.
So instead of relying solely on heating and cooling systems, we're tapping into the power of the building materials themselves.
Precisely.
Wow.
It's a more sustainable and energy-efficient approach to building design.
It's mind-boggling to think about how something as fundamental as heat flow can have such a profound impact on technology and even our daily lives.
It really highlights the importance of understanding materials at their most basic level. When we unlock the secrets of how materials behave, we unlock a world of possibilities.
Well, before we get too carried away with future predictions, let's bring it back to the present.
Okay.
We've covered a lot of ground in this deep dive into anisotropy. What are the key takeaways you want our listeners to walk away with?
I think the biggest takeaway is that materials are far more complex and interesting than we often give them credit for. This concept of anisotropy, where a material's behavior changes depending on the direction, challenges our assumptions, and opens up new ways of thinking about how we design and interact with the world.
We also learned that this directional heat flow is governed by something called a thermal conductivity tensor, a mathematical tool that helps us map out the preferred paths for heat to travel within a material. It's like a heat flow GPS.
Exactly.
And we explored how rotating a material or applying a magnetic field can actually redirect heat flow, demonstrating the power we have to manipulate heat at a fundamental level.
For sure.
We even came full circle to answer that initial question. Why does wood feel warmer to the touch than metal? Even when they're both at room temperature. Turns out it all comes down to the anisotropic nature of wood and its unique grain structure.
It's a great reminder that even everyday observations can lead to fascinating scientific insights.
So to wrap things up, what's the one message you want to leave our listeners with?
Never underestimate the power of curiosity. Keep asking questions, keep exploring, and keep pushing the boundaries of what you think you know. The world of materials science is full of surprises. And who knows, maybe one of you listening will be the next to unlock a groundbreaking discovery.
That's a fantastic note to end on.
Thanks.
A huge thanks to our expert for guiding us through this incredible deep dives.
Of course.
Into the world of anisotropic materials.
Yeah.
And to all our listeners out there, keep those minds curious.
Yes.
And keep exploring until next time.